Good morning, folks. This is the second lecture of week 1. What we like to do today is analyze a block with a central hole, which is intention. Okay, and we're going to look at the multiple planes of symmetry associated with this geometry. So here's the setup. We have a block with a central hole. The dimensions are given here, and this is under axial loading on both sides. Now, if you look at this problem, first thing that you might say is, well, can I just forget about one of these forces at the, for example, left side, and fix that entire face on the left side, and then apply the force F to the right end? The answer is yes, but you're not solving the problem that I'm giving you. Okay, although if the hole is far away from those ends, fixing this end and applying load F here, or applying F on both sides, or applying the corresponding pressure on both sides is not going to have an effect on the stress distribution around the hole if this is long enough, but you have to do the problem that I'm asking you to do, namely left end and right end are both subjected to the force that's given. Okay. Now, if you look at this problem, you see that this problem can be modeled or simulated exactly as it is. But if you also look at it, you realize that YZ and XZ and XY are all planes of symmetry. In other words, all I need to do is to cut this object with these three planes, basically take 1/8 of this geometry, 1/8 of the geometry, and the stress distribution in this 1/8 piece is the same as the one that happens on the right of it, the same as the one that happens below it, and on the left side, etc. So there are three planes of symmetry here. But you might say, okay, why don't I actually not take one of the planes of symmetry? Does it have two planes of symmetry? The answer is yes. So that's going to be 1/4 of the model. Okay, in other words, you just cut it with the, for example, XY plane, and the, in this case, I've done it with the XZ plane. Okay, but no cut in the YZ. So that's going to be 1/4 of the model. Or can I do half of it? Just one plane of symmetry XY. Yes, these are all correct, but I'm asking you to use as many planes of symmetry as are applicable. For example, if this happens to be on a homework or on a test, we can ask you to use as many planes of symmetry, and you must use the one with 3 cuts. Okay? All right. Now, what I'm going to come and do later on, first I apply a force here, okay? And then I'm going to repeat that thing where I apply a corresponding pressure. Now, I want a force, but I'm going to show you what happens with the force and what happens with the pressure. The other thing is that just cutting it is not good enough. You can't just take 1/8 of the model and then say, okay, let's apply load. You have to, these artificial surfaces that are created, these artificial surfaces that are created, the one that you cut by XY plane or the YZ plane or XZ plane, they must be restrained somehow, and those are roller supports or symmetry constrained or restrained, but CATIA does not have something called roller, it's called surface slider. So don't just take a portion of that geometry and pretend that you're all good. No, when you introduce an artificial face into that geometry that you're using, because of symmetry, you have to apply the proper restraint on it. Okay, we'll do that. So let me go ahead and model this whole thing exactly like it is. And then I'm going to split it. You have a choice of making the whole model and then cutting it, or you can, since you know what you're going to be doing, for example, 1/8 of the model, you can create 1/8 of the geometry. I'm not going to go that route. I'm going to create the entire model and cut it 3 ways, and then gradually show you what happens if you actually did not use all 3 planes of symmetry. We'll get there. Okay, so let's go right here. This is a part file. Immediately I close this product file that was created and I start with the part file. Okay, and right away I'm going to save it. I haven't done anything, but I'm going to save it in a folder that if this was a test, you would have to upload for problem number 1 or 2 or 3. So file, save management, save as. I'm going to go to my desktop. I'm going to create a new folder, and that folder, I'll call it problem, or let me put it this way, lecture 2. Lecture 2. Okay? There we are. Good. So let me change the units to tools options. Just to make my job easier, I'm going to use imperial units, namely inches and pounds and things like that. And I think I'm already, if I'm not mistaken, I'm already there, but we'll find out. Maybe not. Okay. So the length is going to be turned into inches. This is a static problem, so I don't need the density. The force is going to be in pounds. That's already in pounds. Very good. Pressure is already PSI, so that's all I need here. Okay, good. Now, on that vertical plane, I will sketch a centered rectangle to make my job easier, right there. And I'm going to give it the dimensions that I have. I believe those dimensions were 2 by 4 by 10. So this is going to be 10 inches. 10. And this is going to be 4. And in the middle, I draw a circle. I think I forgot to write the dimension of that circle in the middle, but that hole in the middle, but I'm going to do that right now. So let's see now. This is going to be, we make it radius 1. Radius 1. Does that look like this? Maybe radius 0.5. How about that? Radius of 0.5. Good. Exit. And then pad it by 2 inches. But because I want to cut it later on, let me pad it by 1 inch in each direction. However, I do mirror extend. Mirror extend 1 inch in each direction, and then this. Okay? Okay, good. Let's apply material to this thing. So apply material. Metal. Metal. Steel on that part. We say okay. Now I don't expect you to go and change the properties, database properties. You can if you want. If you double click on the steel, you see what will happen. The material dialog box is going to open up right there, and you click on the analysis tab. So these are the values that are being used. Now, for example, here I'm saying that, okay, why don't you use 30 million? That's not very far away from 29 million, okay? But anyway, I'll use the material database. This is it. Good. And we click on the floppy. So this is going to be saved. And then we're going to go to Start, Analysis and Simulation, Generative Structural Analysis. So CATIA sees a solid object and immediately it meshes it. Immediately it meshes the solid object. And the size of that mesh depends on some default algorithm that has been written into the code. So it looks at the overall size of the object and says whatever. Now, let me say, okay, change the rendering here. You can see that. If you want to see the mesh, right click, mesh visualization, you say okay. There we are. okay? Now, I told you that we expect you to use as many planes as symmetry. So what I should have done before actually I went into the generative structure analysis was to cut this thing 3 ways, and that's what I'm going to do. So I'm going to go back here and say, sorry, I forgot to cut. No problem. So you don't have to actually close this thing. You can go back to your part there, right there, and then use the saw, which surface-based feature. See that surface-based feature? There is a saw here. It's called split. Now you split this thing with the vertical plane. Doesn't matter which side you pick. You split it with the horizontal plane. Again, it doesn't matter what side you pick. And you cut it or split it with this other vertical plane. And we keep that side. There we are. Now, if I click on the floppy, it's going to save that. And if I go to my analysis file, which is right here, you see that the change has already been made. Now look at the mesh, right-click mesh visualization, or just go to this mesh, right-click, activate, deactivate, and it looks like that. Now, I want to show you how actually this, if you look at it, if you double click on Octree tetrahedron mesh, it says that it's using parabolic element with that size. Now, you can choose linear, you can change the size, but what I'm going to show you is that, let me deactivate this and show you how to create a finer mesh around this hole. And the idea, the rationale is this. The stress concentration is going to be around the hole. In fact, the biggest stress is going to be on the top and the bottom. And if this hole is small enough from your stress analysis course, the stress concentration for a very small hole on the uniaxial loading like that is 3. So whatever pressure you apply at the end, here I'm asking you to apply force, but if you take that force and divide it by that area, you get the pressure. Whatever pressure you apply at the ends, the biggest stress on the top and the bottom is going to be 3 times that. That's what stress concentration for a very small hole, uniaxially loaded like that. So we know that there's a big stress variation around this hole on the top and the bottom point. That being the case, it means that, you know what? I would like to have a finer mesh in this area. Okay? So how do we do this? Let me bring this thing out. This is called Model Manager. There's no way you can miss it. There's a traffic light here. Looks like a traffic light. If you open up the second icon on the left, there's another toolbar here. You can see that. It says local mesh size. You click on this, and you click on that, and you put a size that you like. I mean, if this is what you want, fine. If you want it smaller, well, make it smaller, 0.1. And we say, okay, good. Now, if I say, show me the mesh, you'll see that around the hole, you have a much finer mesh. There we are. You can see that right there. Over here, it didn't change. Now, you can go and change everything, make everything small, but that's killing a fly with a cannon. There's no reason. The only action is around the hole, in fact, the top and the bottom of the hole, okay? Around the hole, and therefore, there's no reason to go and make a finer mesh in this area. Okay, let's deactivate this. Good. Now, at this bottom was a plane of symmetry. That means points on it do not go up or down. That being the case, it means that you can either say no displacement in the direction Z, see that bottom face, no displacement direction Z, but you can move in X and Y. If that is the case, isn't that the definition of a roller? So CATIA does not have a roller where you have your anchor and all these things under the strain. There is a roller, there's a slider surface slider. This is like a roller. The bottom. Okay? And then I can do this thing if you want either 3 times or do it once and pick the other surfaces also. Okay? It's really up to you. I will leave you to decide how you do that. In fact, if you look at the tree, under restraint, I already did this. You see that? I can add to this. This face is on surface slider. That face is on surface slider because these are all planes of symmetry. So now you can see that if you click on the surface slider, it says 3 faces. Well, you could have done this thing individually. Please think about this. Okay, stop the video, think about it, talk to us, or come to the lecture, ask questions. Okay, good. Now, on this face, I'm applying a force. The force is 2,000 pounds. Yeah, but that 2,000 pounds is applied on the 2x4 face, 2x4 face. I don't have a 2x4 face. Remember, I cut it into a quarter basically by planes of symmetry. So on each one of these, so on each one of these pieces, this piece and the one next to it and the one below it and the one below it, there's 500 pounds applied. So force, remember the stops are like that, meshing, restrain, load, or the order, of course, between load and strain can be interchanged. Here we are, distributed force on that face, in the direction y. These are from what we did a few days ago, that you does not forget, in the direction y, 500. So you have to take that 2,000 divided by 4, and there we are. Okay, so save our analysis, file, save management. There is the analysis file, you save as. In that same folder, lecture 2, remember? I'll keep it the same name. Excuse me. Done. Okay, so we saved it, and now we're going to run it. Where is the running thingy? It's in compute. You click on it, say all. It will run, and this is a warning message that you get. That's okay. Now, you want to see the deformation? Deformation is right here. This is the post-processing. Remember, restrain, load, compute, image. Okay? First deformation, just show me the shape without any numbers. Okay, that looks good. Because you take that piece and you apply force to this end, and these are on roller, this just stretches. Now, if you want to look at numbers, you click on that. Here are the numbers. Double click, average ISO, and change the material. Already you can see that the arrows are gone, but these are line colors. I don't want line colors, I want complete shading, material shading. There we are. Incidentally, if you want to see your elements, remember how you do that? You go all the way to the top. Because this box was already checked, it shows you the element. Now, let's look at the stress. There we are. You know, there's something that should bother you, and that is these end points, they don't look physical. In fact, applying a force on this face is not a good idea. On the test or on the homework, do it, because that's what the problem statement says. But for a real life situation, it's better to apply a pressure on this face. And I'll show you how to do that. First of all, what is the pressure? Let's go back here. So we have 2,000 over 8 square inches right here. 2,000 pounds over 8 square inches, or 500 pounds over that square piece, which is 1 by 2 square inches. 500. Let me see now. 500 over. Let me see now. 2,000 over 2 by 4 is 8. Okay, no problem. 2,000 over 8 or 500 over 2 is 250. Okay, so let's go ahead here. I'm going to, first of all, deactivate this plot. Deactivate it. And instead of the pressure on the load, instead of the load force right there, this is the force, it's not the pressure. You delete this, you go and select pressure right there, pressure. See that? Pressure. And you put down 250 psi. That came from taking 2,000 pounds divided by 8 square inches. And this is the surface. Now, if you put a positive pressure, usually means you push into the object. If you want to put it on a tensile load, put a minus sign here, and it's going to reverse us this direction. This is what I want, right? Tensile. Okay, good, good. Let's go ahead and run it. Done. Look at the one meter stress. No longer those artificial, fictitious, displacement at these corner points. And in fact, look at the maximum stress. The maximum stress is right there. The biggest stress is right there. And, our intuition says the same thing, because these stresses that were created here were artificial because of the nature of the loading that we put in there. But on the test, of course, if we ask for force, apply force, unless you are allowed to change it in this problem statement. Now notice that this is 774. Remember I told you for a small hole, the stress concentration factor is 3. So actually the pressure that we applied at this end was 250 psi. You multiply it by 3, you get roughly 750, which is very close to this. Now, a couple of things before we move on, and that is you can always use the cutting plane to cut this thing and look at the stress inside. I mean, there's nothing magic here. We can't see anything unusual, but anyway, you can cut the object just to see that? You can see when you cut it with the object how things look like, okay? In this problem, it really doesn't matter because the biggest stress is on the surface anyways. And by the way, you can animate it. Good. If you want to know the displacement, just go ahead and deactivate this and show me the translation. Very small displacement. Remember, this is 2 inches by 4 inches thick, okay? And you're applying 2,000 pounds on it. It's not gum. This is not going to stretch a lot. And the 750 that you got for the maximum stress at the, at this top point is nothing, because the yield strength for steel, for example, is, roughly of the order of 30,000 psi. 750, nothing. Okay, good. Now, let me deactivate this. You're going to save this. A couple of things before we move on and remove these planes of symmetry one by one. Number one, you might say, well, how do I know what size element do I have to pick? What is good enough? There is no magic ball. Okay, so this has to be done through mesh conversion study. In other words, start with something, run it, look at your stress, the maximum stress, for example. Make sure that that maximum stress is not artificially introduced because of, for example, I put a force here instead of pressure. Now, make the element smaller in the places that maximum stress, it's not really actually the maximum stress. It is where the variation of stress is very rapid. If you look at the color distribution, it was very compressed here. That means this is where the place of action is. So make elements smaller here, run it again, compare. If there is a big change, means chances are that neither one of those are reliable, of course. Not chances, neither one of them are. Make it smaller, and then until things don't change that much. Okay, this is what mesh conversion study is. The thing that you have to worry about is that you have to make sure the stress place that you're looking for is the critical area. It's not artificially introduced because of bad modeling, like me putting force at the end. And yeah, so that's, and you are of course you're dealing with ductile material, for example. Okay, if you're talking about yield strength, then you're talking about ductile material in principle. Now, So what I want to do is now I go and instead of making 3 cuts, I'm going to make 2 cuts. So I'm going to eliminate this cut in the well on this side. How about that? I'm going to eliminate this cut on this side. So do we have to redo the problem? The answer is no. You go to your part. I notice that there are 3 cuts made here. Now this one I want to eliminate. So either I say deactivate or delete. It's entirely up to you. The difference between deactivate and delete is if you ever need it, you have to come back and do it. If you deactivate it, then you can always say activate it and come back. There we are. So now we have used 2 planes of symmetry, the bottom and the side. So if you go to our analysis, you see that first of all, the model has been corrected. Now, the reason it looks like that is that, remember, we put a surface slider on the back, for example. Look at the surface slider on the back. You see that? Now it has 2 faces. And it removes the one. And if you double click on this pressure, it just extended to the whole thing. Because we had the pressure on the left side, but now there is no left or right. They're the same. That's why you have to kind of update it in order to get the result. Now, the problem is this. Let's run it and see what happens. So there is symmetry plane here, symmetry plane here. That's why we have surface slider on it. But the one in the middle is gone because there is no surface there anymore. If you run it, you run into a message. It won't run it. You'll see. This is the standard wording that we get into. But anyway, it's right here. It says, I did not run. Singularity detected. Possible reason, missing restraint or connection. We say, okay, and we close this. Now, you may or may not be able to figure out what the problem is. And first of all, notice that we cannot plot the stress. We can plot the deformation and the displacement, which is total nonsense, garbage, but you can plot it. Now, the reason that there is an issue here is that notice that there's nothing that stops this thing from moving along the x direction. The bottom's on a roller or surface slider. The side is on a roller, a surface slider. Imagine this was a fridge which was sitting on the floor and pushed against the wall, against the vertical wall. You can still slide along here. Now, if you figure it out, that's fine. Otherwise, you can say, okay, Katia, can you tell me what the issue is? So ask for deformation and animate. Now, if you can't see it, no problem, fit it. Okay, so let me see. Let me see that. Fit this thing. Okay, it's somewhere. This model flew away. It's sitting somewhere here. So let me actually do the following. Let me deactivate this. Let me see if I can bring that thing up. There we are. Okay. Now, let's try it again. Activate. Yeah, the thing is that it went too far away again. Let's do the following. Where is this animation? Let me do this. Let me do that. There is a toolbar that I inadvertently closed. I know what it's called. It's called, I can't remember. If you forgot the name of the thing that you accidentally closed, let me remind you how to reset your toolbars. So we say tools, customize, because this will happen to you. Toolbars, restore all contents, and restore all positions. Okay, say okay, close it, close it. The thing that I closed inadvertently was somewhere here. Oh, this one, analysis tool. Okay, this is the one that I accidentally closed. So let me delete this. and do it again. Uh, the deformation. What is this? I've got images under images toolbar. That's the problem when you close one of these. You have to go get it. Images. Okay, there we are. Okay. All right. Good, good, good. Images and animate. You see, it's going as a rigid body in this direction. So we have to stop that. Now, how do we stop that? First of all, deactivate this. I want to say one of these points should be stopped from moving in the X direction. Now, clamp, we know what it is. Clamp means in all three directions, it should be stopped. Well, that's not the case. I'm stretching this, so I want it to move. Surface slider, we know where it is. It's this bottom one. It's this bottom one, which is called user-defined restraint. User-defined restraint allows you to fix in a specific direction, a particular item. So, by the way, notice that these were checked. That's why I was getting that warning messages, those warning messages, because it says, hey, you checked something, but those are not even degrees of freedom. But anyway, the support is this one point. I can select this point, or I can select any other point and says, do not move in the direction X. Do not move in the direction X, direction 1. You see that? Stops it. Stops it means gives you 0 value. That's what it means. Let's run it now. No longer that message. Just give me 1 second. And by the way, I didn't get that warning message because I removed that, those rotational degrees of freedom. They're not part of the solid element. Now, deformation, it should stretch. It didn't run away. But the problem is that because last time you interrogated CATIA, it reduced the scale for you so you could see on the screen what happened. So go to this analysis tool, amplification magnitude, set reset or default. There we are. You can see that. And now animate. It just stretches. Good. Numbers, displacement. You click on it. Very small numbers. These numbers didn't change and they will not change. You should not change. Average ISO. There we are. And you can still animate it if you want. We already know. And the stress. Click on it. There we are, 777. Biggest stress, top and the bottom. Good. You say, okay. Now, you might say, can I take this away? Can I take this thing away? This symmetry plane away. Well, let's go ahead. Let's go to the part. And that will be this one. Right click, deactivate. Okay, we go back to our analysis. There we are. Okay. By the way, you want to look at the mesh, no problem. You go there, activate the mesh, you can see it all the way around that hole. They're all finer, and it will be, you can see that. There we are, you see that? All the way around the hole. Good, good. So deactivate this mesh. Okay. Now, notice that this surface slider does not go there, but as soon as you double click on it, it will adjust it and expand to the other side. Oh, I guess not. Okay, so select this, 2 of them. Right. Okay, good. Now, if we are doing it like this, and you put a load here, what? The load must also be on the other side. No longer surface slider. So we go pressure on that face. Good. Now, Let's think about it for a second. As it is right now, remember this restraint is there. So let me remove that for you. Let me delete that. Let me delete that. I'll show you what happens. Now notice that this is like a fridge door, a fridge sitting on the floor, and somebody's pulling it this way, somebody's pulling it that way. This can move as a rigid body on the floor. In fact, if I run it, it'll come back and say, I can't do it. It'll bomb out. It is in static equilibrium, but it can move because there is a 250 psi there, 250 psi there, but it will can be moving on the floor. We can see that. In fact, you can plot the deformation. You see that fit. Okay, let me change the scale here. Let me change it a lot smaller, maybe I don't know, maybe 100 fit. In fact, let's animate it. You can see that this moves as a rigid body. Okay, right there, we can see that it's moving. So we say fine, no problem. So here's what we're going to do. I'm going to deactivate this, deactivate that, or delete it, deactivate it, whatever you want. Just put it back in. Good. Now, one point we say, hey, you cannot go in any direction, X or Y. You can't go in the Z direction anyway because of that surface light. So let's click on this. That one point, for example, the one on the bottom, does not move in direction X and Y. So this can still hinge about that. So to take away that hinging effect, we say another point cannot move, for example, in the direction X. So another one cannot move in the direction X, right there. Just X. We say okay, and we're gonna run it. This time it will run because the rigid body motion has been taken away. Okay, good. Can I look at the deformation? Activate. And if I animate, I don't see anything because when you interrogated CATIA, it actually reduced the scale to the extent that actually you could see something on the screen. So go and change this thing to default. There we are. And now animate it. You see, it stretches. Without these constraints, it would just move as a rigid body on this floor, for example. Good. Plot the stress. So deactivate this, activate the 1 meso stress, right there. Yeah. Okay, 784. Okay. A little bit different, but in the same ballpark, less than 1%. Now, you might say, okay, what if I use no planes of symmetry? Say, fine. Let's go here to our part and deactivate this last one so that there is no planes of symmetry whatsoever. So we go back to our model. Everything has been accounted for. Notice that, first of all, there's a couple of things. So for example, the surface slider is completely gone. There is no surface slider at all. If I leave it here, there's going to be a problem. So I'm going to delete that. And on purpose, I'm going to delete these 3 strings also. User-defined strings also. Pressure is okay right here on that face. Pressure is okay on the other side. See that? That's okay. And we're going to run it and watch it bomb out. We will see that it will bomb out. Can I see the deformation? It'll fly away probably. Oh, yeah, right there. So let me actually try to fit this thing. Yeah. And the reason is that, let me deactivate it. Okay, deactivate this, delete it, deactivate it, and fit the whole thing. Good. This whole object can just float in the space. So what I'm going to do is I'm going to apply something called the 1, 2, 3 rule. The 1, 2, 3 rule is one point will not allow it to move in any three directions. That kind of stops it here. Another point will prevent the rigid body rotation. And the third one will just rigid body translation. So here's what I mean. You click on the user define a particular point. For example, this point cannot move in any of the three directions. This point, that's another point, cannot move in the direction, let's see now, Y and Z. Another point, not in the direction Y and Z, which means that it can still hinge about that line. Okay, no problem. And a third point, this point, for example, these are not going to be random anymore. You have to think about it. This point cannot move in the direction Z. This will take away the rigid body motion. This will take away the ability to float. This will make it allow it to rotate about that line, and this will prevent that rotation. So we say okay, and lo and behold, if you run it, it's going to run. So notice that actually the one with 3 planes of symmetry was the easiest one to do here. You didn't have to do a lot of thinking. As we started to take away the number of planes of symmetry, there's more and more and more that you have to do. Okay, good, done. So let's look at the deformation. Here's the deformation. Change the scale, by the way, because you may not see anything when you animate here because it took away, I actually do see it. So let's change the scale, the amplification back to default, here, default. That's good, actually, it was good. And you can look at the deformation. It just stretches and shrinks in the direction X. You can look at the stress. Let me deactivate that. 1 meter stress. Right there, 780. Biggest stress, top and the bottom. Stress concentration of 3 for a small hole. You can see that. Okay, let's move back. Good, good. Can I make a cut? Yeah, sure, I can make a cut. But let me do the following. Where's the cutting plane? This is the cutting plane. Okay, so let me move this thing actually a little bit. Right there, you can see that. And then you can rotate it and things like that. Now, the reason it's so slow because we have a lot of elements, we have very fine mesh around the hole, we have parabolic elements, so, you know, these all slow things down. And as a matter of fact, look, 780, right? 780. Let's go ahead and make this thing from parabolic to linear. And see what the effect is. Remember here it was 780 at the stress, so run it. 780-ish because when we remove the number of planes of symmetry, that's changed a little bit, but not by much. Okay, and let's look at the 1 meter stress. You see, 680, that's a lot of change. Going from linear to parabolic, it gave you about 10% difference. Okay. Here, for a cut, it probably is a lot easier to move the cutting plane because, yeah, you can see that already. Let me there. Yeah, you can see that. When it was parabolic, there were too many elements, etc. And then you can cut this thing in different directions. Not like that. Hang in there. Yeah, right there. And by the way, you can say, oh yeah, don't show me the clipping. It just shows you, or don't show me the cutting plane, or show me the clipping only, okay, etc. View section only. These are all things that you can do. Now, cancel that. Let me go here and remove these restraints. Delete it, delete it, and delete it. Now, remember, when I took this and ran it, it bombed out, and it will bomb out again. You'll see that. Because this thing can float in space. There, you can see this. Now, there is something in CATIA which does this 1, 2, 3 rule for you automatically. And that is this thing. See? Isostatic restraint. If you click on this, it just puts this thing there. Just puts this thing there. And when you run it, it will not bomb out. And I'll tell you what happens when you do this. Done. Show me the stress. Right there. 685. Remember? Okay. Now, so what exactly happened when I put this anchor there? Let me deactivate this plot. When you put that anchor there, it goes and picks 3 nodes and applies that 1, 2, 3 rule for you automatically. And if you don't believe me, here's what you're going to do. Let me change the rendering to wireframe. You'll see why. And put the cursor there on the isostatic, right click, restrain visualization on mesh. Say OK. There is going to be 3 points, 3 nodes here when the 1, 2, 3 rule has been applied. So let me zoom in. Hey, here is one of them. 1 and 2 have been fixed. There must be another point where all 3 of them. Ooh, right there. 1, 2, 3. There must be another point where only 1 degree of freedom has been fixed. So now that's going to be hard to find it, but let's see if we can do this. You know what? I'm going to change the background color here. Tools, options. Under visualization, display, visualization, where is this? The background color, make it white, and it may be easier to find it that way. Then we are looking for a blue cursor, blue. See, this was the one for all 3 of them, right there. You can see that. It's going to be hard. There must be 1 or just 2 of them, or just 1 of them have been fixed. Somewhere must be. Oh, this is the one with 1. You can see. Oh, this is the one with 2, right? 2 degrees of freedom. Where is the 3rd one? There must be another one. I cannot find it, but there is a 3rd one. Promise. Let's check. Not there. Not there. And I'm running out of time. Okay. So the 1, 2, 3 rule has been applied automatically for you in CATIA. It's just that I cannot find that 3rd point. You have to look for it carefully. And it's buried somewhere in the model, and I don't know where it is. Let's take maybe another minute, see if we can find it. So in a problem like this, you can either do the 1, 2, 3 rule manually yourself, or use that anchor. And I have some other videos, not for the course here, but in my channel where I have done other problems, talk more about this business of anchor, etc. So that's bothering me because I cannot find that guy. Yeah, somewhere. Look at this corner, maybe. No. Ah, boring. Yeah, that's okay. Anyway, good luck. See you in the lab tomorrow.